A client connects through a load balancer to a server and database, secured by an encrypted TLS tunnel. But if an attacker drops a forged token through this tunnel, they bypass the back-end encryption entirely, instantly gaining full database access. The Open Worldwide Application Security Project classifies this specific mechanism as A07 for 2025, Authentication Failures. Recent datasets show over 1 million recorded occurrences of this vulnerability class in the wild. It encompasses 36 distinct common weakness enumerations, or CWEs, ranging from basic password flaws to complex token manipulation. Modern application security depends on the rigorous, ongoing maintenance of identity state. To understand how this breaks down, we have to look at 2 distinct failure points: how an application validates initial credentials, and how it manages continuous session state after a user logs in. Spending resources on advanced back-end encryption is an architectural failure if the application cannot mathematically verify the user passing through the front door. The first phase of authentication is initial validation. The most basic, axiomatic model is a simple username paired with a secret password. Attackers no longer rely on random brute force guessing to break this pairing. Instead, they use credential stuffing. By feeding massive, pre-compiled datasets of usernames and passwords from previous data breaches into automated tools, attackers establish a highly accurate baseline for their attacks. To adapt to basic security rules, attackers deploy a technique called password spraying, or hybrid credential stuffing. They take a known, breached password and iterate on it to predict a user's next logical choice. The terminal script takes a baseline password and algorithmically mutates it, appending sequential numbers and years to the end of the string, firing continuous login requests. The logic bypasses filters, predicting the updated password, and unlocks the server. When an application fails to rate limit these automated vectors, it falls victim to CWE 287, improper authentication. Automated attacks exploit user habits, but an even more basic deployment failure completely nullifies the need for algorithms, leaving default credentials intact. Classified as CWE 259, leaving hard-coded passwords like admin in a production environment provides a baked-in backdoor. It allows an attacker to bypass complex authentication logic without writing a single line of code. Relying purely on human-generated passwords actively degrades cryptographic entropy. Human sequencing and memory habits are inherently predictable to algorithms. Despite this predictability, enterprise IT policies continue to force users to rotate their passwords every 90 days and adhere to arbitrary complexity requirements. This vault mechanism illustrates the mathematical flaw. When you force frequent rotations, users cope by making minor, predictable adjustments, like changing Spring 24 to Summer 24. With every forced reset, the internal entropy actually decays, feeding the exact hybrid stuffing attacks the policy aims to prevent. Look at the updated NIST Credential Management Framework. The infographic strikes through forced rotations and arbitrary character rules, replacing them with 2 distinct requirements. The first new rule mandates length. Expanding a password requirement to 8 or 10 minimum characters exponentially increases mathematical entropy, rendering brute force computation unfeasible. The second rule requires active database cross-referencing. Applications must query new passwords against known breached databases via APIs. If the password exists in a breached dataset, the system rejects it. These password rules support mitigation strategy C7, Secure Digital Identities, which shifts the burden of proof away from human memory entirely. Securing initial access requires multi-factor authentication as a non-negotiable architectural component for any system handling sensitive data. MFA integrates physical, cryptographic hardware proofs, such as FIDO2 security keys, directly into the validation flow. The user must possess the physical item to complete the handshake. While standard authenticator apps provide an additional layer, hardware keys generate unphishable cryptographic signatures, offering a strictly higher level of mathematical assurance. Securing the front door means moving initial credential validation off flawed human memory, requiring algorithmic cross-referencing and physical cryptographic possession. Effective authentication operates as a continuous lifecycle that extends through the entire duration of the user's session. This split-screen flowchart shows how architectures manage post-login state, server-side versus client-side stateless. In the server-side model, the server generates a randomized session ID, stores the state, and sends a reference ID wrapped in a secure HTTP-only cookie. The primary vulnerability here is CWE384, broken timeouts and session fixation. If a user logs into a public terminal and closes the tab without logging out, the session remains active on the server. To secure server-side sessions, the architecture must actively invalidate the session upon logout and enforce absolute timeout parameters driven entirely by the server, severing access after a set period of inactivity. Transitioning to the right side of the diagram, modern applications increasingly rely on client-side stateless models, primarily using JSON Web Tokens, or JWTs. A JWT contains three parts: a header, a payload, and a signature. The header dictates the algorithm used, while the payload transmits user state, defining their identity and privilege roles. The third section, the cryptographic signature, acts as the only proof of the token's integrity. It proves the server actually issued the token. An attacker can intercept the JWT and alter the encoded payload text, changing their role to admin. If the application reads the modified payload without verifying the cryptographic signature, it grants the attacker elevated access. Validating a user's initial credentials offers no security if the subsequent session state can be forged or remains active indefinitely. This zoomed-out flowchart illustrates the complete end-to-end model required to defend against OWASP A07 vulnerabilities. The client submits a lengthy password alongside a FIDO2 hardware proof. The server cross-references the password, validates the hardware, and issues a cryptographically signed JWT with a strict, visible countdown timer. Identity, mapped through strict algorithmic and cryptographic validation, serves as the only true modern security perimeter. We remove our reliance on flawed human entropy by implementing multi-factor hardware proofs and aligning with the updated NIST frameworks. We lock down the post-login state by treating session lifecycle management and token verification as strict cryptographic operations that attackers cannot bypass. Secure applications maintain safety by continuously and mathematically verifying a user's identity across the internal architecture. If you found this architectural breakdown helpful, subscribe to the channel for more technical security analysis. Let me know in the comments which OWASP vulnerability you want to see deconstructed next.